Welcome to today's deep dive. We are jumping into this absolutely groundbreaking paper today.
Yeah, it really is.
It's from July 2026 by the ABOT World team, and it's titled Infinite Interactive World Rollout on a Single Desktop GPU.
Quite a title, right.
Right, but the mission for this deep dive is, well, it's pretty wild. We're going to explore how AI is evolving, like moving away from just generating those static passive video clips you see online.
Yeah, the cute 5-second dog on a skateboard videos.
Exactly. Moving from that to simulating entire, interactive, persistent worlds, like worlds that you can actually play in. Real-time, running on just a single consumer graphics card.
Which is honestly a massive leap.
It really is.
Yeah.
And to grasp why this is so huge, I want you to just think about looking at a high-definition photograph or a beautiful video clip.
Right.
There's this invisible wall there. It's stunning, sure, but it is entirely frozen. If you reach out to, touch the water in the frame, your hand just hits glass.
Exactly. You're locked out.
But imagine if you could touch that glass, and instead of stopping, your hand just goes through. The water ripples around your fingers.
Yeah.
You step into the frame, you look around, and you realize the visual isn't just a picture anymore.
It's an actual place.
Right, a place that actively responds to you.
And taking that step, going from a passive image to a responsive place, that is just a monumental shift in computer science.
Yeah.
Going from video generation to true world simulation is this epic systems-level challenge. The researchers behind this paper, they couldn't just tweak some existing AI model.
They had to build it from the ground up.
Well, they had to solve 4 major bottlenecks, basically all at the same time.
Yeah.
First, they had to figure out how to get the exact right kind of data. Second, how to represent user control. Third, how to stop the AI from having a complete meltdown and hallucinating over long periods.
Fever dream effect.
Exactly. And finally, the hardware problem. They had to make this entire simulated universe run fast enough to actually be interactive on standard equipment.
Okay, so let's unpack this. Let's start with that first bottleneck you mentioned, the data.
Right, the matrix, basically.
Yeah, because if we are trying to build a world that actually responds to, say, me pressing a key on my keyboard, I'm assuming we can't just feed the AI a million hours of random YouTube videos and hope it figures it out.
You've hit on the core issue perfectly. Passive video, it just shows an AI what the world looks like.
Okay.
But it provides absolutely zero context for why things are happening.
Oh, I see.
It's like watching a car drive by without knowing there's a steering wheel inside. The AI doesn't know that the camera moved forward because a user physically pushed a thumbstick forward.
Right. It just thinks the world is moving on its own.
Exactly. And without that action data linking a physical input to a visual output, the AI can never learn controllability. It fundamentally needs to understand cause and effect.
So where do they get data that shows both the action and the result, like side by side?
They actually had to build a massive multi-source data infrastructure, and it combines 3 distinct types of information.
Okay, what's the first one?
The first is AAA video games.
Oh, well, that makes sense.
Yeah, games are perfect for this because they provide what we call ground truth controlled data. The system records the screen, sure, but it also records the exact millisecond a button was pressed to make that character jump or turn.
So it gets the exact pairing. Button press equals jump.
Precisely. Now, the second source is simulation engines, specifically tools like Unreal Engine and environments built using 3D Gaussian splatting.
Okay, I have heard that term thrown around a lot lately. 3D Gaussian splatting.
It's a big buzzword right now.
Yeah. What does that actually give them in this context, though?
In simple terms, it gives them perfect photorealistic geometric control.
Geometric control.
Right. Splatting is a really efficient way of rendering 3D scenes from 2D images. So by using these simulation engines, the researchers can generate mathematically perfect environment.
Okay.
And that lets the AI observe exactly how light, shadow, and geometry behave when a camera moves through a space, but without any of the messiness or unpredictability of the real world.
Got it. So we have video games for the button press data and simulations for perfect geometry and lighting.
Right.
What was the third source then?
The third is actually internet video.
Wait, really? But you just said internet video doesn't have the button presses.
It doesn't. But even with games and simulations, you still need massive real-world diversity.
Oh, to make it look real.
Exactly. You need natural lighting, shaky camera movements, weird environments to help the AI generalize. But like we said, internet video doesn't come with a log of someone's keyboard strokes.
So how do they link it?
The researchers used a technique called pose estimation to generate these things called pseudo-labels.
Pseudo-labels, meaning they are basically faking the button presses.
I mean, in a highly mathematical way, yeah.
How does that work?
Imagine a drone video flying down a city street. The AI analyzes how the buildings and the street shift from frame to frame. It calculates the complex geometry of that movement and reverse engineers what the joystick movement must have been to create that exact visual shift.
Oh, wow. So it mapped out the camera movement.
Exactly. It mapped that math back to simulated button presses. And to keep everything consistent across all three of these data sources, they mapped every single action to standard keyboard inputs.
Like WASD.
Exactly. WASD for moving around and IJKL for rotating the camera.
That is just brilliantly simple. Just raw keyboard inputs.
Right.
But I was reading about how they actually gathered all this game and simulation data. They didn't just hire 1,000 people to play games in a basement all day, did they?
No. They built something called World Explorer.
Right, World Explorer.
And this is honestly one of the most vital innovations in the entire pipeline. It's an autonomous, agent-driven collection system.
So it's an AI playing the games.
Exactly. Think of it as an AI bot that plays the games and navigates the simulations 24/7. It just endlessly wanders through these virtual environments, capturing the video, the camera poses, and the keystrokes all simultaneously.
So traditional AI training, it always seemed to me like forcing a student to read a massive textbook of data you collected months ago.
Passive learning, yeah.
Right. But this World Explorer system, it sounds more like giving the student a controller and saying, go play, and whenever you fail a test on a specific level, I want you to spend more time playing that exact level.
That is a great way to put it.
Because the paper mentioned it uses closed-loop training feedback.
Yeah. To take your analogy a step further, the student is basically writing their own textbook as they play.
Oh, wow.
That closed-loop feedback transforms the whole data collection process from a static, one-time dump into an active servo system.
An active servo system.
Right. The World Explorer agent actually monitors the main AI model. If it notices the model is really struggling to render rain correctly, or maybe failing to understand third-person camera angles, the agent actively seeks out those specific scenarios.
In the games.
Yes, in the games and simulations to gather more data. It constantly shapes the data it collects to surgically fix the model's specific weaknesses.
But surely the agent messes up sometimes, right? Like, I mean, in a video game, characters clip through walls, or the camera glitches out, or the character just dies.
All the time.
If you feed that glitchy video to the AI, won't the AI just think that's how the universe works?
It absolutely would. If an AI learns from a glitch, it assumes the glitch is a fundamental law of physics.
Right, because it doesn't know any better.
Exactly. So to prevent that, the team built a really rigorous multi-stage quality filtering pipeline. They run 14 deterministic checks across 6 different dimensions on every single piece of data.
14 checks.
Yeah. They actively strip out user interface overlays, they delete death sequences, they remove any clipping glitches, and on top of all that, they use vision language models to analyze the video and add structured text annotation.
You mean they have another AI basically watching the video and writing down like, this is a person walking through a snowy forest.
Precisely. This ensures the main world model isn't just blindly memorizing pixels. It actually semantically understands the context of what it is rendering.
Okay, so through all of this, games, simulations, internet video, World Explorer, we finally have the perfect data set.
The foundation is set.
Right. The AI fundamentally understands that pressing W means the scenery should move forward. But knowing the rules and actually generating a continuous world are two very different things.
Very different.
Which brings us to the second massive bottleneck. Because if you ask a standard video AI to generate a clip for more than, say, 10 seconds, it usually turns into a terrifying fever dream.
Oh yeah, the nightmare fuel.
Yeah. The dog on the skateboard suddenly grows a 5th leg, the skateboard turns into a loaf of bread, and the whole world just melts.
The technical term for that melting effect is autoregressive drift.
Autoregressive drift.
Okay, and to understand how the researchers cured it, we have to look at how these models actually generate video in the first place. The team started by building what they call a bidirectional teacher.
A teacher model. Okay, what makes it bidirectional?
It means the model looks at the entire video sequence all at once.
The whole video.
Yes, it processes the past frames, the present frame, and the future frames simultaneously to ensure everything makes perfect logical sense.
Oh, I see.
And this produces incredibly high-quality, visually consistent video. The problem is, it is completely useless for a live, interactive environment.
Right, because in a video game, the engine can't possibly know what button I'm going to press 10 seconds from now.
Exactly. It can't see the future.
It can't see the future, so it can't process future frames.
Right. Real-time interaction requires a causal model, a system that only looks at the past to generate the very next frame.
Okay.
So they had to transition the deep knowledge of this heavy, future-seeing bidirectional teacher over to a lighter, faster causal student model.
And I saw in the paper they used something called ODE distillation for that.
They did.
Distillation usually means boiling something down to its essence. Is that what is happening here?
That's a really great way to visualize it. ODE stands for ordinary differential equation.
Okay.
In standard generation, an AI takes many, many small mathematical steps to turn basically static noise into a clear image. ODE distillation essentially forces the student model to learn the shortcut.
Oh, a shortcut.
Yeah, it teaches the student how to jump straight to the final, clean image that the teacher would have produced, but skipping all that heavy, multi-step processing, it compresses all the heavy lifting.
That sounds incredibly efficient. But wait, doesn't jumping straight to the answer bring us right back to the fever dream problem, that autoregressive drift you mentioned?
It absolutely does. When the causal student starts generating frame after frame on its own, tiny microscopic errors occur.
Like compounding interest.
Exactly like that. Frame 1 might be 99.9% perfect, but frame 2 is based on frame 1, so the error compounds.
Right.
By the time you get to frame 500, those microscopic errors have multiplied. The model drifts into a mathematical state it has never seen in its training data.
It panics.
It panics, and the world either freezes entirely or dissolves into static.
So how do you stop a model from panicking when it gets confused? The paper highlighted this solution called long forcing.
Yes, long force.
How does that actually keep the AI grounded in reality?
The mechanism behind long forcing is something called distribution matching.
Okay.
During training, the researchers don't just show the student perfect short video clips. They actually force the student to generate incredibly long sequences and let it make mistakes.
Wait, they let it hallucinate on purpose during training?
Yes. They expose the student to its own long, error-prone, hallucinated rollouts.
Why would they do that?
Because then they bring in that extended horizon bidirectional teacher we talked about to provide corrective supervision.
Oh, the teacher comes back in to grade the paper.
Exactly. The teacher looks at the student's messy, hallucinated output and essentially says, I see you're drifting off into a weird reality here. Let's nudge the entire distribution of your output back into the realm of plausible physics.
Wow.
By constantly matching the student's long-term output to the teacher's stable logic, the student actually learns how to recover from its own compounding errors.
It learns how to self-correct.
Right. It learns how to stay stable over massive time horizons.
That is fascinating. It's like letting a driver safely spin out on a test track so they learn how to steer out of a skid,
Perfect analogy.
rather than just hoping they never hit a patch of ice in the real world.
Exactly.
But there is another hallucination problem I want to bring up. In most AI video, if a character turns around or maybe walks behind a tree, they come out the other side looking like a completely different person.
The shape-shifting problem, yeah.
Yeah. How do they keep the characters visually consistent over time?
That requires something called identity preservation. To solve this, the researchers use canonical reference images of the character, and they store them as identity memory tokens.
Okay, identity memory tokens.
And then they apply something called negative temporal rope indices to those tokens.
Okay, you're going to have to translate negative temporal rope indices for me because that is a mouthful.
I know, it is heavily technical. Rope E stands for rotary position embedding.
Rotary position embedding.
Right. Usually, these embeddings help the AI keep track of the forward flow of time. You know, what happened in frame 1, frame 2, frame 3.
The timeline.
Exactly. But by using a negative temporal index for the character's reference image, they are mathematically locking that image in a secure vault outside of the normal timeline.
Oh, outside of time entirely.
Exactly. The timeline of the world keeps moving forward, but the character's core identity remains anchored.
So the AI doesn't forget what they look like.
Right. The AI can always reach outside the flow of time to double-check exactly what the character is supposed to look like, no matter what environment they just walked into.
That is brilliant. Okay, so we've solved the data bottleneck.
Yeah.
And thanks to long forcing and identity tokens, we have an AI that understands cause and effect and won't lose its mind after 30 seconds.
The brain is built.
The brain is built. But here is the third major bottleneck.
The speed.
The speed. Because if I press W Shay, and it takes the AI 10 minutes to calculate and render the next frame of this beautiful, coherent world, it's just a fancy painting.
Right, it's not a simulator.
You can't play it.
No, and this brings us to the absolute necessity of full-stack co-design.
The stack.
Yeah, for a long time, the AI community thought making generation faster just meant tweaking the algorithm, making the AI guess the image in fewer tries.
Right.
What this paper proves is that achieving real-time interaction is a hardware and software engineering problem at every single level of the stack.
And the deployment specs they achieved are just staggering. I actually have to read this directly from my notes because it's so crazy.
All over it.
They got this model to stream 720p video at up to 16 frames per second with only a 1.2-second delay between you pressing a key and the very first frame appearing.
That latency is incredible.
And they did it all on a single standard NVIDIA RTX 5090 desktop GPU.
A single consumer card.
Right. And the whole thing uses under 19.3 gigabytes of VRAM. To me, that is like cramming an entire symphony orchestra into a phone booth and still expecting them to play a Beethoven symphony flawlessly.
It shouldn't be possible.
How do you fit an infinite universe into 19 gigabytes of memory?
Well, to use your analogy, you can't just ask the orchestra to play faster while they're crammed in the phone booth.
Right.
You have to fundamentally redesign their instruments.
Okay, where do they start?
First, the team tackled the VAE, or the variational autoencoder.
What does the VAE do in this pipeline?
So AI models don't actually think in pixels.
Okay.
They think in a highly compressed mathematical space called a latent space. The VAE is basically the translator.
Oh, I see.
Its job is to take that compressed math and decode it back into the visible pixels you actually see on your monitor.
Right.
But the researchers found that the standard VAE decoder was eating up way too much memory and processing time just drawing that final image. So they created something called Light VAE.
Light VAE.
Yeah, which heavily prunes the decoder. It streamlines that translation process so it barely leaves a hardware footprint at all.
So they basically shrank the translator. What else? Because I imagine RAM management is a nightmare when you're generating an entire world on the fly.
It is an absolute nightmare, which is why they implemented memory-aware scheduling.
How does that work?
If you tried to load this entire massive AI model onto a consumer graphics card all at once, it would immediately crash.
It's too big.
Way too big. Instead, the system dynamically swaps neural network modules in and out of the GPU memory exactly when they are needed for a specific calculation.
And then flushes them out.
It flushes them out the millisecond they aren't needed anymore. No part of the model is allowed to just sit there taking up valuable space.
Wow. And I also noticed in the paper they mentioned dropping down to FP8 precision.
Yes, FP8.
Now, I've seen FP16 and FP32 in standard models. What does moving to FP8 actually do for the speed?
FP stands for floating point. In simple terms, standard AI models do their complex math using 16 or 32 bits of data for every single number. It's highly, highly precise, but it requires massive memory bandwidth. By forcing the AI to do the math with only 8 bits, which is called low-bit quantization, they lose a microscopic fraction of precision, but they effectively double the speed at which the GPU can process the visual data.
Double the speed.
Yeah. And they combine this with an optimized attention mechanism called Sage Attention 2.
Sage Attention 2.
Right, which helps the AI instantly figure out which parts of the image to focus its computing power on. They literally optimized every single layer of the software to match the physical limits of consumer hardware.
That is just incredible. Which brings us to the final and honestly most mind-bending section of this deep dive, emergent reality.
This is the best part.
Because we built the engine, we trained the brain with perfect data, and we optimized the hardware to run at lightning speed.
Right.
But when you actually sit down at your keyboard and press the W key, what actually happens on the screen? Does the world actually feel real?
To rigorously answer that, the researchers ran the model through a testing benchmark called World Roam Bench. They measured action controllability, meaning, does the character actually move when you press the button?
Right.
They measured trajectory following and visual quality, and the model scored incredibly high across the board. But the stress tests, that is where the true potential is revealed.
The long horizons.
Exactly.
They didn't just test it for a few seconds. They let this model run for hour scale and even day scale rollout.
Uninterrupted.
Uninterrupted.
Yeah.
Generating an interactive video, frame by mathematically generated frame, based entirely on user input for an entire day.
And it didn't crash.
And the environment stayed coherent. You could just keep walking, keep exploring.
But staying visually stable isn't actually the most profound discovery in the paper.
Really? What is?
The true breakthrough is what the researchers call emergent physical plausibility.
Yes. Oh, man. The examples in the paper are just incredible.
They really are.
They describe a moment where a person is walking and pushes a cardboard box out of the way. They describe footsteps in a puddle leaving temporal ripples in the water.
Water displacement, yeah.
A character walks through snow and leaves persistent tracks behind them. If you walk in a first-person view into a solid wall, the wall stops your motion.
It acts like a wall.
If a character walks into a metal railing, they bump into it instead of phasing through it like a ghost.
Yeah.
I have to stop and ask for clarification here. Did the researchers program a physics engine into this?
No.
Is there code somewhere saying, if character touches wall, set velocity to 0?
That is the crucial point to understand. No, there is absolutely no hard-coded physics engine.
Wow.
There are no collision boxes. There is no code telling the system how gravity or solidity works.
So, wait, the neural network just learned the laws of physics on its own?
Yes.
Just from watching video?
Yes. And if we connect this to the bigger picture, it is staggering.
It's unbelievable.
The model derived these physical constraints purely from its large-scale interactive video experience.
Because it watched so much of it.
Exactly. Because the AI analyzed millions of hours of cause and effect, seeing that characters in games don't walk through brick walls, seeing that snow naturally displaces when a foot presses into it, the neural network actually internalized the underlying laws of physics.
It didn't just learn to draw a wall.
No, it didn't just learn how to draw a picture of a wall. It mathematically learned the concept of solidity.
I'm just trying to wrap my head around the scale of that. It learned the physical rules of our universe simply by observing cause and effect at scale, and now it can recreate those rules on demand in real time.
It's emergent physics. It's beautiful.
So let's bring all of this together. The ABOT World Zero model proves that simulating infinite interactive worlds isn't just some far-off sci-fi concept anymore.
It's here.
By combining active closed-loop data collection through World Explorer, utilizing long forcing to keep the AI from hallucinating over time, and engineering these brilliant full-stack optimizations like SP8 Precision and Light VAE, we can actually generate playable realities on a standard desktop GPU. And for you listening, whether you're a hardcore gamer looking at the future of entertainment, a software developer, or just someone curious about the edge of technology, this fundamentally changes the landscape.
Completely.
The line between playing a coded video game and interacting directly with a neural network's imagination is about to completely vanish.
Right. They're becoming the same thing.
You aren't just navigating a pre-rendered math anymore. You are exploring a reality that is being dynamically generated in response to your every single move.
Which raises an incredible and honestly perhaps even slightly profound question to leave you with.
What's that?
Wow, if a software model can accurately internalize the physical rules of our world, things like collisions, gravity, object permanence, and material displacement, just by watching and interacting with simulated video data.
Yeah.
What happens when we take these deeply knowledgeable imaginations out of the computer?
Okay.
What happens when we hook these world models up to the physical brains of robots?
Real-world robots.
Exactly. Could these infinite AI-generated interactive worlds become the ultimate training ground for real-world embodied intelligence?
It really makes you wonder what happens when the physical robot realizes it doesn't have to hit the glass wall either.
Absolutely.
Well, thank you for joining us on this deep dive into the ABOT World paper. Next time you look at a beautiful photograph, just remember, pretty soon you might be able to press W and step right through it. Catch you next time.